All right, let's talk about what is a limit. So, a limit, the notation for it is looks like this. So we have a limit notation as x approaches some number of a certain function. So let's take a look at the function x plus 2. Now we already know what this limit is going to or we know what this function looks like already. Here's 2. And we're going up 1 over 1. Now, if we talk about the limit as x approaches c, let's look at the limit as x approaches 1 of this function. So now we're defining c at a specific point at 1 here. Now, although this isn't a perfect graph, I'm going to try and adjust it so it is more accurate with what the actual graph looks like. Okay, so at x is 1, here's 1. We know our y value is 3. But that's not necessarily what we're looking at when we're talking about the limit. When we talk about a limit as x approaches some number, we are looking super close to 1 from the left and right limit. Now, what is a left and right limit? A left and right limit is when we talk about some number to the left of the graph of 1 in this example. For example, 0.999 and 1.001. 1.001 is to the right of 1 and 0.99 is to the left of 1. And this limit notation is saying as we get closer and closer to 1, what does it look like the function f is going towards? In order to do that, we need to look from left to right, going towards x equals 1, and from right to left as x is getting closer and closer to 1. But the important thing to note about this notation is that this is not the same as just plugging in f of 1. It's not always going to be the same. We are simply just looking at what it looks like our function is going towards, what y value it looks like our function is going towards, not what the actual y value is. So, in order for a limit to exist, this is the definition. If the limit as x approaches c of f of x exists, then the limit as x approaches c from the left of f of x equals the limit as x approaches c from the right of f of x. This is saying that we need to look from left to right what it looks like the y value of the function is going towards, and we need to look right to left to see what y value it looks like the function is going towards at x equals 1. Now, if they're both going to the same y value, that means the limit as x approaches c exists, because it looks like in this example, from left to right as we get closer and closer to 1, looks like the function is going towards the y value 3. And from the right, when we look right to left, it looks like as we follow the function in, we're getting closer and closer to the y value of 3. Now, why is this important? Well, let's take a look at this example. We have y equals 4 over x minus 1. Now, if we take a look at the limit as x approaches 1 of y, first we need to both consider the limit as x approaches 1 from the left of y and the limit as x approaches 1 from the right of y. Now, let's start with as x approaches from the left. We go left to right, and we can literally put our finger on the function and see what it's going towards. Now, what happens as we get closer and closer to 1? Here's our y value 1. Our function is going towards negative infinity. Now, what's happening when we go right to left and we put our finger on the function? We see that our function is going towards positive infinity. Because the limit as x approaches 1 from the left of y does not equal the limit as x approaches 1 from the right of y, we can say that the limit as x approaches 1 of y, just in general, does not exist because the left and right limits do not equal each other. Now, we will find out later in a different video that when we have a limit as x approaches some number that is equal to negative infinity or positive infinity, that actually correlates with a vertical asymptote. And we can see right here that it looks like our lines are going to get closer and closer to, and this side negative infinity, and this, or we're getting closer and closer to 1 from the left and from the right, but it's never actually going to touch 1. It's going to go infinitely down, but never actually touch 1. Now, you see this graphically, but let's check it out algebraically. So we already know that this limit does not exist. But let's take a look specifically. How could I, if I didn't know what this function was going to look like, how can I find the limit as x approaches 1 from the left of, I'll just put a 4 over x minus 1. Now, we said in this last example that a number to the left of 1 could be 0.99999. So let's plug that in. And now, why can't I just plug in 1? Well, if I were to actually plug in 1, I would end up with 4 over 1 minus 1, which is equal to 4 over 0. We know we can't, this is undefined. We know we can't divide by 0. So the limit allows us to look at the function behavior that gets super close to x equals 1, but not actually x equals 1. That's why we have to take a look at the left and the right. So instead of plugging in 1 to our function, let's plug in 0.999 minus 1. Now, what is that going to equal? That's going to be 4 over 0.001. And we need to remember that this is just an idea of what we're plugging in, because we can get infinitely close to positive 1 from the left. Instead of 0.999, we could have 0.999999999. And we keep adding 9s, and we're going to keep getting closer and closer to 1 without actually touching 1. We're getting so close that we are almost, we're getting so close that we're almost dividing by 0. But we know it's not actually going to be 0. It's going to be, I forgot this is negative. We know it's going to be some super, super small number. So I'm just going to put super small number. And we know, since it's from the left of 1, that it's going to be negative. So it's going to be negative some super small number. Now, what happens when we divide by a super, super, super small number? We end up with a super, super big number. This 4 is pretty irrelevant. But what we need to remember is this negative. Because if we were to have, the smaller we get, the more we are going to be multiplying by 4 to end up with a bigger number, if that makes sense. So if this was like 4 over negative 0.001, we would actually be multiplying by 4 times 1,000. Now, instead of dividing by negative 0.001, what if we did 0001 over 4? Well, then we would end up with negative 4. Oh, sorry, actually I should just put positive 4 times negative 10,000. And see, as we start dividing by smaller and smaller numbers, we're going to keep getting bigger and bigger numbers, infinitely big. So we end up with this going towards negative infinity. Note it's negative because we have some positive number divided by a negative number. Therefore, we should end up with a negative number. And as we look at the graph, we can see from the left, our function is going towards negative infinity. Just from here, we can confirm that there is a vertical asymptote. But it is very interesting to think about, okay, now what happens as we look at the limit as x approaches 1 from the right? We already know it's going towards infinity, but a vertical asymptote could also correspond to a function that looks like this, sorry. So they both are going towards negative infinity. So let's take a look at that. So let's do the limit as x approaches 1 from the right of 4 over x minus 1. Well, let's think of a number that's close to 1 but not actually 1. How about 4 over 0001 minus 1? Now we'll end up with 4 over 0.0001. Note how this is very similar to our previous thing, the previous example, as we're looking at the limit as x approaches 1 from the left, only this bottom part is positive, and that's because we have a bigger number minus our 1 than what we had before. So this is going to end up being positive, and as we keep dividing by a smaller and smaller number, we're going to get bigger and bigger numbers, and that's going to go towards infinity. So here, not only can we confirm the not only can we confirm what's happening at x equals 1 from the left, from the right, but we can also confirm that there is a vertical asymptote right here.